Okay, so for question 2b, we're given two drink dispensing machines modeled as model 1, you go to a start node, a coin is inserted, and then you have the option of having coffee or the option of having tea. And in model 2, we can see you go to a start node, you insert a coin, and you either go down the left hand side where you can get a coffee, or you can go right in which you can get a tea. So obviously from a user's perspective, you want to use model 1, where you can insert a coin and you have a choice of a coffee or a tea, as opposed to on the right hand side where the machine actually decides for you. If you insert a coin, you're going to get a coffee or a tea, and that is it. So what paths are available, or what available paths exist for both models? Well, we can see that the only paths you can have is you insert a coin, you can get a coffee, you insert a coin, you can get a tea. So they are actually our only two paths, are get a coin, tea, coin, coffee. That's our maximal number of paths. Can LTL satisfy all these paths? Well, LTL is a linear execution, so we can see that we can start in state 0, insert a coin, then we can get a coffee, state 0, insert a coin, or get a tea. These are our only two possible LTL paths, and yes, it satisfies both of these maximal paths. So yes, can CTL formula satisfy all these paths? Well, we go to CTL, we can go to coin, we can get tea, coffee, coin, coffee, coin, tea. Yes, so we can also satisfy. Can LTL distinguish between model 1 and model 2? Now here is the question. So LTL, as we saw, is a linear time execution. So we can only have coin, state 0 to S1 to S2, or state 0 to S1 to S3. Insert a coin, get a coffee, insert a coin, get a tea. That is all. So from them two executions, can you tell which model you've actually used, which machine you've actually used? And the answer is you can't. You only know you've inserted a coin and you've got a coffee, inserted a coin, you've got a tea. You don't know which machine has done this for you. It could be either or. So the answer is no here. And this is where CTL comes in handy. So can CTL distinguish between model 1 and model 2? So to answer this, we'll use which logic is best to answer the question. A coffee action is possible after any coin action. So once you've inserted a coin, you are able always to get a coffee. You're always available to get a coffee. So again, we're on about possibility. So if we go down to CTL, this would be your formula for that question. So for all paths, always, once we insert a coin, it implies that there exists a path where eventually we can get a coffee. So the fact that you would see exists a path almost always rules out LTL. Not always, but it's just a good indicator. So for all paths, always, coin implies that there exists a path where eventually we can get a coffee. So if we go to our first model, once we insert a coin, so for all paths, so again, so we have our path here, we'll call it path 1. So for all paths, starting from S1, after we've inserted a coin, there exists a path where eventually we can get a coffee. So yes, we can see here from his path, we can always, there exists a path where we can get a coffee. So this is true. Now, if we go to machine 2, as you can see, these are modeled off this machine, same as these two machines. We insert a coin, we can go to state 1 or state 2. So here we'll call this path 1 or path 2. So for all paths, always, once we insert a coin, there exists a path we can get coffee. So now from this path, there exists a path we can get a coffee. Yes. So for all paths, we're going to check path 2 always, so this has to hold as well. We insert a coin, yes, and there exists a path where you eventually get a coffee. And that is not true. We can only get a T on this path. So this does not hold for model 2. So we can see if this holds that we must have used model 1. So this is how you can differentiate. So a coffee action is possible after any coin action. For this to hold, we must use model 1. And LTL is not able to show that, only CTL is able to show that. So that is the answer to question 2b. Now, if we were to model this, so we have our drink machine. Let's zoom in a bit. Now, again, this is the same as our models that we have here. So we have state 0, state 1, state 2, state 3. State 0, we just call it a start node, so this is where our model starts. State 1, we inserted a coin, so coin is true. State 2, we've selected coffee, so coffee is true. Atomic proposition is coffee. In state 3, we wanted a T, so atomic proposition T is true. Now, always, for all paths, always coin implies exists a path, eventually coffee. So if you actually look at the bottom of the lab sheet, you'll see the syntax that allows you to do implies. You'll see the box and the DIA. So after a constraint, a successor is necessary, or after a constraint, a successor is possible. So we'll use the box for this example. We're going to say you have to be able to get a coffee. So we're saying for all paths always, same as here, box coin. So once you have coin, this tells me once I have coin, the successor must be there exists a path where you can get a coffee. So all paths always, once you get a coin, there exists a path. It implies that there exists a path, you eventually get a coffee. So that is the same as here. You can replace this with DIA as well. We check that, and this model holds. So whenever we get a coin, the successor, there will always exist a successor we can eventually get coffee from this path. Let's just check. It does not work with DIA. Yeah, so it has to hold. So box is the one for this. And lab machine 2, we'll zoom in. Copy, you can see. So we use the same formula. Of course, we're using T, and question we use coffee. We can easily change that to coffee. And we check it, and it says no, we have a failure. From state 0, for all paths always, once we insert a coin, the successor, there exists a path where eventually we can get coffee from a successor. Or that is not true, as you can see from state 0, we insert a coin, we can go here, and now we can only get a tea and not a coffee. So that shows the example, that shows you how you can use implies. And that's the question for question 2. The answer for question 2.